Hey everybody, welcome back to the PyTorch 2.0 Q&A's Ask the Engineer series. If you've been following the series, welcome back. If you're new to the series, this is your opportunity to ask your burning questions.
If you've been following the series, welcome back. If you're new to the series, this is your opportunity.
Apologies there, we had some hiccup. So if you've been following the series, welcome back. If you're new to the series, this is your opportunity to ask questions to our esteemed panel here about the new features that were launched or announced at the PyTorch conference on 2.0. Today we have two exciting topics, TorchInductor and PyTorch 2 backend integrations. So we'll take the first half of the talk to live stream to talk about the first topic, which is TorchInductor, and then we'll do the PyTorch backend integration. Before we get started, let's do a quick round of introductions, and then we'll jump deep into the topic. And this is a Q&A series, so please put in your questions. This is your show. This is all about answering your questions on this topic. So let's do a quick round of introductions. I'm Shashank. I'm a developer advocate at Meta. And who wants to go first?
I can go. So my name is Bimbao. I'm a software engineer from the PyTorch compiler team working on TorchInductor. Yeah, Natalia?
I'm Natalia Gimelshain. I also work at Meta on TorchInductor compiler and other parts of Lawrence Stack.
Awesome.
Hello, I'm Sherlock. I'm also from Meta. I'm working in PyTorch core team and working on the PT2 stack.
Okay. Yeah. Hi. I'm Akon. I'm from the Intel, and I'm from the my team is Intel PyTorch team, and I'm focusing on the PyTorch DL compiler. Yeah.
Awesome. Welcome everyone. So we have quite a star-studded cast, in my opinion. Engineers from Meta and Intel. So this is an awesome opportunity to ask questions. Let's get started then with the first topic, which is TorchInductor. Some of you may be familiar with this from our launch at the PyTorch conference, and this may be a new topic to some of you. So let's start with some quick introductions on what it is. So let's start, Natalia or Ben, who wants to go first? So let's define what is TorchInductor.
So TorchInductor is a PyTorch native compiler that actually takes a whole graph and trying to compile to a program with a better performance. So that's my very brief understanding. Natalia, you want to say something?
Yeah, that's a pretty good description. So let's dive directly into the slides where we give a little bit more details about it.
Yep. Okay, then I'll get started. So I suppose the screen is up. So today it's our honor to do a deep dive into TorchInductor. So I will start with a very brief overview of TorchInductor software stack, and then I will cover some design principles there that might help people to understand some of the designs and code in TorchInductor. And after that, we are gonna talk into different technologies being used there. I will cover the IR part, the intermediate representation, and Natalia is going to cover some of the optimizations in TorchInductor. Like for example, she's going to touch like scheduling fusion and also codegen part. And also because we have a codegen for the CPU backend as well. So we have invited Akon to give a talk on there. So all right, let me first start with this very high level overview. So TorchInductor is a compiler, right? And what's the input to that compiler is really coming from something called AOT autograd and also prime torch. And because we are building TorchInductor as a training compiler, so we need AOT autograd to help us to capture both forward and backward graph. And what PrimTorch does here is it helps us to decompose the large amount of PyTorch operators into a much smaller set. So it's orders of magnitude smaller with its help. So after the input is ready, then TorchInductor is going to do lowerings to lower those operations and programs into something understandable by TorchInductor itself. And usually in the compiler domain, it's called an IR. And with the IR ready, then TorchInductor is going to do optimizations. And it's also called scheduling, actually, inside of Inductor. And we do things like fusion, tiling, and memory planning. And again, Natalia is going to touch more details there. After all those optimizations, we have two options to generate the different backend code. One is Trident, one is C++. So some of the design principles we have when we were thinking about the TorchInductor. So the first thing we want to do, make sure is it really like PyTorch native. So which means we want our users to feel like this is as close to the PyTorch Eager as possible. People can have a very good user experience from Eager. And also we designed and implemented the TorchInductor in Python. So it's a Python first principle. So in reality, we feel it can boost our productivity. And also we hope it's more friendly for our OSS community to play with and contribute to the code base. And third principle is really like we took a breadth first approach from the start, which means like instead of focusing on a few like specific operators, we want a compiler to be as general as possible to cover as many operators as possible. And that this principle also applies to the backend choice we have. Like instead of focusing on GPU, we do have both CPU and GPU.
So, Bin, quick question, if you don't mind, while
Yeah.
we wait for more questions from the audience.
Sure.
So, what is the purpose of this compiler here? Usually, a compiler is to improve performance, right? I mean, that's one of the goals of a compiler. Mm-hmm. So, the reason we built TorchInductor is it mostly for getting better performance out of your PyTorch program?
Yeah, exactly. And then we feel like there's still a big performance gap in the training domain. Mm-hmm. So we want to build something to help to boost the performance there.
And this is for training and during the deployment phase, or primarily focused on the training aspect?
It's mostly for the training, and deploy. Can be deployed as a part of the whole system, right? Mm-hmm. But then the deploy usually depending on your specific environment. Like certainly
depending on where your target is, whether it's an embedded device or a GPU or a CPU or something else.
Yep.
Sounds good. Thanks.
I would like to add that there are a lot of deployment inference solutions that are pretty good. Onyx runtime, for example, or TRT for GPUs, or AI template that's also been developed at Meta. But for training environments, there generally has been a dearth of interesting compiler solutions. So that's why we are undertaking this project.
That's true. That's true. Awesome. Thanks.
Okay, then I will continue to the next page. So as I promised at the beginning, so I'm gonna jump into a few details about the IR design. And first of all, the IR in TorchInductor is pretty special in its form. It's called a defined by run, and it's defined by run loop level IR. I will show you with another slide what I really mean by that. And also the IR is pretty generic in the sense that we use SymPy to build like symbolic shapes, and then and also guards to help us to be more general in the optimizations we are performing. So here's one example for that defined by run IR. Like for example, if we have this like permute plus this slide operation, then it actually becomes like an inner function. Like it is basically a Python function, right? And then as you can see here, the index is is symbolic, and then we do a load for the first one, operand, and then load for the next operand, and we can do an add of those two. And this inner function is going to be stored as a member of this IR class called pointwise. And of course, we have all other kind of IR classes like reduction and some other ones. So what's special here is like if you go through Inductor's code base, there's a lot of places doing this kind of ops.load, ops.add, ops.store, this kind of ops.something, right? And the special thing about that is those operations kind of can be are overloaded for different phases, overridden for different phases. Then we can essentially keep the same IR, but we have them to perform different things when we're at different stage of a compiler. So that's what we mean by define by run.
Here's a question, Ben, from the audience, and
Sure.
You may be answering this a little later. I think you will be answering this a little later, but I'll ask it anyway.
Okay.
And you can choose to decide if you want to answer it now. So the question is, I love that the compiler is in Python. Just curious, how much performance influence does it have compared to written in C++? So I imagine for a CPU target, how much performance difference would you see versus using the compiler versus, I guess, hand coding directly in C++?
Natalia, do you want to take the question, or do you want to wait later?
I think we, in the end of this presentation, and you can look at it now, there are links that are comparing the performance we're getting with Inductor to what we are getting with pure PyTorch. And pure PyTorch pretty much has hand-coded in C++ kernels. So, but the question was that compiler is in Python, like Python creates the subsequent runnable that will be called, but this runnable is in uses actually efficient CUDA representation or efficient C++ representation. There will be more on that later.
All right, should we move on?
There's another question. Okay. I'll ask it again. You decide if this is the right time in the presentation to answer this. Sure. So where is size 0 defined? This is from Daniel. Where is size 0 defined? Actually, how are the ranges extracted from that function definition?
The size 0 is like we look at the actual input, and then if we have a way to map it to a symbolic variable, and then so it's not a specific value as I mentioned, right? Like, but then also we if it's a static shape, we know the hints, like what this coming from, what's the original one. I actually have another slide coming up, so maybe that will help to explain. Yeah. Yeah. Again, as I said, like although we may take an input, look at the size, and we know, oh, it's a concrete value there, right? It doesn't mean we will use that and to optimize our program, because that will lose the generality. We can get into like too specialized for certain cases, but also there are value to specialize on a few cases, right? Like here I mentioned maybe on 0, on 1, and then also on like the sameness. While we're doing that, we also make sure we have guards to guard the correctness, and then yeah. So basically that is how we do that, and we do that for shape, for the size, also for strides, right? And that's we have ways to propagate those guards by looking at expressions. I don't know if it answers the question, or maybe Natalia, if you have something to add.
So the size in the previous IR function is closed over from the surrounding definitions. So when there is a lowering for that operation that's been showed, we actually, in the lowering, extract the sizes from the inputs, and then the inner function is just closed over from the surroundings.
All right, with that being said, I'm going to hand this over to Natalia.
I'll talk a little bit about scheduling fusions and what fusions Inductor can make, and then I'm going to switch to demo, which I hope will tie together a lot of the things that Ben and I have talked about.
So Natalia,
there
I have
are
a few more questions. Do you want to cover your topic and then address them, or do you want me to few more questions?
Let's switch to the questions then.
Okay. So, Karan, thank you for your questions. We have a couple of them, and I know you were at yesterday's live stream, which was about distributed training and FSDP. So, I guess this question is related to distributed training. So, the question is, can you comment on how the distributed operations like collectives fit into the compilation process? For example, the DDP talk mentioned future plans for allowing traceability of collective ops. What does it mean from the compiler perspective, and how does the functionalness of the operator impact the optimizations that a compiler can do? For example, the process group ops aren't functional today in that they mutate the inputs and returns. Couple of different sub questions in them, but yeah, you want to take them, Natalia?
I'm afraid I'm not the best person to answer those questions, and including the collective operations into the traces optimized by compiler is very much a work in progress. So I cannot say a lot about what's been done already. But yes, the future as we envision it is that, yes, collective operations will be traceable, they will be exposed to the compiler, and compiler will be able to analyze the things that are going on and schedule the collective operations so that they are performed in the optimal places. As for collective operations frequently being mutating, yes, that's a problem, but sorry, I cannot tell more. Probably yesterday's webinar was a better place to dive deep into those questions.
Yeah, thanks, Karan, for the question. And I think Will, who was doing the yesterday's session, he did share his information. If you had questions, I mean, I think we're all here to learn and take feature requests and feedback. So feel free to reach out to Will as well in the information he shared. Thanks, Natalia, for that response. We have one other question, the last one on the stream so far, which is, will this boost CPU performance to the level of a GPU without a compiler? Will this basically enable more training capabilities for the CPU to the level of not bothering to enable GPU for training? Ooh.
I don't think so, to be honest, because speeds and feeds of GPU are just much, much better than speeds and feeds of the regular CPU. But I'll defer to A10 to maybe he knows about some super capabilities of the CPU that would be unlocked.
The question that's a tough one to answer, is it, Wang? Go ahead.
Yeah. Mm-hmm. Yeah, echoes Natalia's point. Yeah, for some computation-intensive operators, I think it is hard to beat or to match the GPU performance. But for some element-wise operators, I think the performance may be could be on par with GPU. Yeah, but beside that, it is specific. It depends on the GPU's CPU specific instructions. For example, for the Intel, the latest Sapphire Rapids, it provides some systolic instructions, provides the matrix multiply instructions to accelerate the bfloat 16 and into 8. Yeah, it provides other performance room for their optimization. Yeah, but I for some specific scenarios, I think it is hard to beat to the GPU performance. Yes,
that was a very good response. Thanks. I mean, fundamentally, GPUs are throughput devices, right? I mean, if you have a throughput based problem, then it's hard to take a CPU to beat it. If you're really compute bound and you can really fully consume a GPU, it's hard to. They're serve slightly different purposes. So thanks. I think there's a follow up here, which are fusion specifically for this from Daniel again. Are fusion specifically for inference or training also? I ask because preserving intermediates for the backward pass can be tricky.
Yes, as been said, the PyTorch 2 stack is aimed primarily at training. And yes, it's absolutely correct that preserving the intermediates for the backward pass is kind of a tricky problem. And that's one of the things that AOT Autograd is solving. Shashank, did we have webinars already specifically focused on AOT Autograd, or are we planning those? Because it's a very interesting topic that deserves its own deep dive.
That's a good point. I don't think we've had one yet. I need to check, but I will share the schedule at the end of the presentation. And I think yesterday's talk, we did talk a little bit about that, specifically for in the context of distributed training, where they had separate graphs for forward and backward, and figuring out how to reconcile that in the context of distributed training. But yeah, I will share the upcoming where upcoming streams are, so people can join in at a future date if we have. But we do plan to keep having more streams with specific topics like these. Another question here in
but
this.
Let me then answer this question very briefly. So we use AOT Autograd to trace joint forward and backward function. So first we create a function that has both forward and backward in it. And then we use a min-cut partition algorithm that allows us to save as few intermediates as possible and still be able to recompute all the necessary data that we have in the backward function. So the end result of this AOT tracing is a separate forward function that has a lot of outputs, not just the output that was the output of the network, but also all the intermediates that we are going to use, and the backward function that takes in all the necessary inputs and computes the backward. And they are most memory efficient because we are taking pains to transfer as few intermediates from forward to backward using the min-cut partition algorithm.
Awesome. Thanks, Natalia. I missed a question that was asked before the fusion question. Apologies, audience one. So does the FX graph need to be fully functionalized before lowering by inductor?
It doesn't need to be, but Inductor can support some of the in-place operations, but it's on a best effort basis, so it could have some bugs. But again, AOT Autograd is taking care of the functionalization for us, so the graph that we are getting from AOT Autograd is functionalized, and Inductor is producing efficient and correct code for that.
Thanks. We've answered all the questions that are on the stream right now. So if you want to continue.
I think I just want to skip the slides here and switch to the demo. Shashank, can you? Oh, okay. So in this demo, I'm actually showing a small program where I'm just computing a simple softmax operation. I optimize it with the PyTorch 2.0 compile function, and then I'm just calling this optimized function with some input on the device. And let's see what happens here. Here is my command line. It's very simple. The only thing I've added in the beginning is an environment variable that will allow me to print the FX graph that Inductor is getting. But otherwise, I'm just calling this a very simple program. And let's see what happens. It takes a bit of time to initialize CUDA on the device. It takes a bit of time to go over this even simple program and compile it, but here is the output. So the first thing that I'm printing here is the FX graph that we got from the lowering. If you remember, the original program had the softmax function, but as been said, using PrimTorch, we are reducing those more complicated functions into a series of simpler things. So first, we convert the element into the computation type because making computations in half is just very inaccurate. Then we compute the maximum, then we compute the sum of exponents, and finally, we normalize all the elements in our initial array with the results of this. So again, the first thing you see is the results of the decomposition, as been mentioned. We need PrimTorch so that compilers don't need to know how to support all the 2000 PyTorch functions. And here is actual generated GPU program that performs this computation. Like, let's skip over all those inputs. That's not interesting. And here we see a pretty readable, pretty understandable Python code that's generated. So first, we are reading the values from the input array. If you remember from Bean's IR slide, there were ops load, and this load instruction is pretty much what ops load is getting translated into. So the first loop is computing maximum, the second loop is computing the sum of exponents, and finally, in the end, we are applying those pointwise transformations and outputting the result. Again, the nice thing about Inductor, I think, is that all the stages are pretty much hackable, debuggable, and understandable. We wanted to look at the FX graph. It's very easy to use the environment variable to look at the FX graph, or there are other debugging tools that would output those intermediate representations in the convenient form. We want to look at the output code. Output code is not some low-level thing that will take a very long time to understand. It's something that you can look at and pretty much have a good idea of what's going on and which operations were used.
That's amazing. It's not a black box, right? That's what you're saying, that you can actually see everything. Is there a situation where a user would actually go and modify this beyond what TorchInductor spits out as part of the IR?
I don't think that for users it's really necessary to go in and modify things, because we try to make the code that we produce pretty optimized. But for developers, for people who actually work on Inductor, having these convenient intermediate stages and debugging tools is pretty nice.
Makes sense. Makes sense.
And with that, for the remaining couple minutes, I want to give the stage to Wang so that he can tell us more about the CPU support in Inductor.
Yeah,
Unless there are some questions that you want me to answer now, Shashank.
There's one question. Kazuaki, Inductor generates Python code to drive a sequence of ops. Do we see overhead for inference by driving ops by Python instead of native instructions?
Yes, we would see an overhead in inference. For GPU, actually, Inductor is also using CUDA graphs. So CUDA graphs are a pretty amazing tool to reduce the overheads or hide the overheads completely. So in that case, whatever Python code Inductor generated will actually be eliminated once we've captured the CUDA graph and are replaying CUDA graph. For CPU, and one can talk about it more, but we are working on actually creating this glue code in C++ and not in Python to reduce the overheads.
Awesome. Thanks. I hope that answers the question, Kazuaki. And again, there's a Q&A, so feel free to put in questions along the presentation. Wang?
Yeah, okay. Okay, this is the C++ and OpenP backend. This backend provides support for x86 CPUs and a wider range of other devices. It could make sure that the inductor, but just not support GPU, also for CPUs. Currently, we are focusing on optimizing the x86 CPUs, but it does not mean we cannot support other devices, because we have reserved and exposes their interfaces to other devices. Therefore, it should be a limited effort to support other devices, right? So the next is the current status for the AP32 inference for both single-thread and multi-thread scenarios. Compared to the eager mode of the pure PyTorch, we could see that we observed a significant performance improvement for TorchBench, Hugging Face, and Team. And in the next step, we currently we only focus on the AP32 inference, and in the next step we will expand the data types, we will support bfloat16, IP16, and quantization, but not just IP32 only. And we will optimize for the training performance since and currently, for the PyTorch 2.0, we are focusing on the inference mode. And in the next step, we will continuously optimize both inference and training by, for example, extend more vectorized ops coverage, right? And to make sure support more scenarios. Okay. Yeah, so that's the CPU C++ backend introduction. For more technical details, we can discuss in the PyTorch dev discuss PyTorch org and then on the GitHub. Okay.
Awesome, thanks. There is a question. This was about the from Karan as a follow-up. Are CUDA graphs dynamic versus static? So not a question for Wang, I guess, but Natalia.
CUDA graphs are static, so unfortunately they require the sizes to be constant and to not change between the iterations.
Awesome. All right, thanks. So we're at the halfway point. We can transition to PyTorch to backend integration, which is an exciting topic for I guess vendors and others. So please keep the questions coming in while we transition to the next topic. Were there any final things to share, Natalia, Ben, Wang, before we fully transition?
I want to highlight the dashboard. The link is at the end of the slide that demonstrates current improvements of PyTorch 2.0 compiler stack compared to under more results compared to the current performance of PyTorch IR. And I think it's pretty exciting that PyTorch 2.0 stack can speed up the models that have been beyond reach of the previous compiler attempts.
And I'm going to share these links in the stream as well. I'm doing this right now. I guess a last question, and we'll hard stop, move to the next topic, which is from Karan again as a quick follow-up. Will that always be true? The staticness of graphs, he's asking.
The CUDA graphs APIs as provided by NVIDIA require that all arguments remain the same. There are APIs to patch some of the arguments. So in fact, in some limited situations, probably CUDA graphs could be enabled for dynamic shapes, but it's pretty fragile. So I wouldn't recommend diving into this unless you want to spend a lot of time.
Awesome. Okay, let's move on to the second topic. We have Sherlock. Let's go ahead and introduce the topic, and again, keep please putting in your questions for the folks on the live stream. Go ahead, Sherlock.
So hello guys. So what I'm going to talk about is about the backend integration in the PT2 stack. So you all know, like, PT2 introduced this compiler stack, and we have our own in-house compiler called Inductor, and then you have also listened to the talk just now. But like this compiler stack is open for community. Basically, we are welcoming the backends to build on top of the PT2 stack. So by backend, we actually mean a lot of things. It could be like external libraries like XLA or Onyx runtime, or it could be hardware vendors like ASIC developer vendors to build on top of it. So actually, we know that a lot of backends have already indicated interest to integrate deeply into the PT2 stack, and this talk is intended as an information node to show like where to start. So if there's any takeaway from this talk, like we want to tell you like what is the integration point that is available in the PT2 stack. And the second thing is like what are the offset, the IRs that you need to work with. So this is the mental model, like mental map that I want to put out in to begin with. So this is basically illustration of the PT2 stack. So you have listened to, there's something called Dynamo. Dynamo is going to produce a FX graph by doing the Python bytecode parsing. And then there is some lowering component called AOT autograph that will also return another graph, but it's on another IR called A10 and Prims IR, it will also give you like the backward graph, which we'll dive more into detail later. And basically, we say this is the backend integration interface that like we would recommend backends to consider. And basically, it's an FX graph in A10 IR. That's one place to integrate. And the second place to integrate is within Inductor. As you have just seen, like Inductor supports multiple codegen backends. One is C++, one is Triton. You can also bring your own like codegen backend into Inductor. But like the focus of today's like tutorial is more at the FX graph level integrations. So like for more like information about how to integrate into Inductor, like you probably need to just reach out to us and ask for more details. So
Sure.
that's
quick question. In terms of who this is for, right? Based on your diagram, it seems like so there's two components to it. The front end, a user interacts there, and the back end is typically, as you mentioned, like hardware vendors or other, you said XLA and few other tools like NVFuser, mostly hardware vendors and others who want to consume, I guess, the IR from the PyTorch, right? Who want to accelerate on their hardware or accelerators and so on. So really, what you're describing is the interface that a vendor could use. Is that right?
Yes, like this is for backend developers.
Okay. Not the end user who would actually be using PyTorch.
Yeah.
Okay.
Yeah, this is more for yeah.
Thanks.
Cool. So let's dive into the demo. So to start with, like this link should have been shared to the public, so you can follow along throughout this talk. And so to start with, let's just ensure that we install the PT2.0 from the nightly and assert that this is 2.0. I have did that already, so I'm gonna skip step. And for the demo today, I'm just going to use a very naive...
Can I pause and just make an announcement? I guess for everyone, everything we're discussing is PyTorch 2.0 features, which is not GA, but it's available in the nightlies, as you showed, right?
Yeah.
So if you want to try it out, I think, go get the nightly version and you can try out these features, but they're not generally available right now. So there will be, bugs along the way, I guess. Did I say that right?
Yep, but you need to use nightly.
Go ahead.
Right, so the model we're playing around with today is a simple linear layer like this, followed by an activation. Usually it's ReLU, but let's just make it a little bit more interesting. Let's call it a JReLU activation, and that's it. And we create the model and then create a sample input with a batch size and some like feature size. And now we reach the entry point of the acceleration, which is the torch.compile, which is introduced in the PT2. Natalia have just shown you that you can use that to accelerate training, and that's the main use of it. But the compile interface also accepts argument called backend. And this is where backend developer can bring their own backend and plug into PT2. So the backend is a Python function here, and there's a few contracts between PT2 and the backend. And basically, the contract says, okay, like you need to implement a Python function where it takes two arguments. The first argument is a graph, right? This is the graph module produced by Torch Dynamo. And then you need to, like many backend would prefer to, would like to work with a static graph, and this is the graph to start with. And the second input is a sample input that will be passed into the your backend need to work with, and you can rely on the sample inputs to do analysis, etc. So like in this particular example, I'm just going to print out the graph and then show you what's happening. So there's no actual compilation happening here. So let's go ahead and run this model. So as you see here, the graph here passing here is actually produced by Dynamo. Okay, and I have just mentioned that the IR produced by Dynamo is called Torch IR. And by what I mean by Torch IR is that it's basically very similar to the Torch API level calls. So the torch.nn linear now becomes a call module call, which is like self fully connected layer, and then the ReLU is mapped to this like torch.nn ReLU. So our recommendation is that like the torch level IR is not exactly a very like friendly IR for you to integrate backend with, mostly for its complexity. So in the torch IR, there is, if you're familiar with like FX concept, there is call function, call module, call master. It could be non-functional. Like even for a single operator, there's many interface, like many forms of the API. Like take convolution as an example. Like a convolution, we actually have 6 forms of convolutions in the API level, but eventually it will all got mapped into a single A10 level convolution call. So that's why we say, yeah, like torch level IR, it's not very clean to work with. Another thing I'm just going to point out here is that the sample input passing to the toy backend is something called fake tensor. So I won't dive into too much detail about fake tensor, but just to raise the awareness that like when you get the sample input, this is a fake tensor. This is it's kind of like a regular tensor, except that it doesn't have the storage binding to it, and when you pass the fake tensor to an operator, it actually doesn't do any like actual computation, but instead it's more like for propagating the shape and d-type and other characteristic of the tensor along the graph. So I think we'll have another talk to dive more into the fake tensor. So stay tuned on that talk. But this is just to call it out that sample input here, it's not real tensor, it's a fake one. Okay, so I've just told you that torch level IR is not exactly the right level to integrate. Then what is the right level? And this is where we need to talk about AOT autograd. So AOT autograd does a lot of things, right? AOT autograd captures the forward and the backward. If you want to support training, you have to be plugged under AOT autograd. That's where you get the backward graph. Another thing is it will lower from the torch level IR to the A10 or Prims IR, as I'm about to show you soon. Another thing is like inside AOT autograd, we do functionalization. So it will remove all these in-place mutations, out variant ops from your graph. Why? Because backends and compiler usually prefer to work with a like functional form of the graph, and this is like we do this through functionalization. And finally, like the whole graph has some good properties that I know backends will love. The graph, the tensors in the graph are populated with metadata, meaning that they have shape and d-type that backends and graph transformation can rely on to optimize. So just like before, like we still gonna passing the, we're gonna expand the implementation of this our previous toy backend. And in the toy backend here, we're just gonna explicitly invoke AOT autograd. This is not turned on by default. Sorry, you still have to do that manually. But the AOT autograd has a very similar structure as the Dynamo. Basically, it will accept forward compiler, and it's have the same contract as the Dynamo. Basically, it accepts a graph module, a sample input, and then you need to return a callable that has the same signature as the graph module. Essentially, the callable is your compiled version of the graph, right? So for demo purpose, again, I'm not doing any compilation here, but if you were to do it, to implement anything here, you should do it here, like plugging your compiler at this level. And let's just take a look at the graph produced by AOT autograd and how could it, like, how is it different from the previous graph? So let's run this, and it produced 2 graphs. Like this is the forward graph, and this is the backward graph, as I said. So in the forward graph, remember previously we have 2 ops. There is a linear, and then there's a ReLU. And the torch level operators kind of are lower to a next level called A10 ops. And in this case, the linear is lower to A10.t, short for transpose, and then there's an A10.addMM, right? And then the JLU, which was previously the torch level JLU, now becomes the A10 JLU, right? So these are the kind of graph that has been lowered into the A10 level. And like basically like this is the operator level abstraction where backends can implement the kernels for, right?
So Sherlock, there are a couple of questions, but I want to ask you a question first. Could you show the graph that you showed at the beginning, the flowchart?
Yeah.
So far, I don't see it yet. So
oh, you mean like the
flowchart at the very top? Yeah. So far everything you've discussed is above the line, right?
Yes.
Above the line. So you've not yet discussed the integration interface, and everything Natalia and Ben covered was also below the line, how they integrated with the output. Okay. Just for my mental model of what's going on. Okay.
Yeah. So we have reached the output of AOT autograd.
Excellent.
And it's our recommendation that backends integrate with FX graph in A10 IR. And it's also the level where Inductor plug into PT2 stack.
Excellent.
So yeah.
So in some ways, what Natalia and Ben and Wang spoke about is consuming the or using the integration layer that you're going to present, right? So they're your customer, if you will, so to say.
Right.
Okay. So there is a question. This is from Mark. Could it possibly be used to help compile optimized modules, maybe through compiling Torch IR to LLVM IR for embedded devices, with federated learning being the main goal? Ooh.
Right. So like torch level IR is still a little bit too high level. So if you were to lower, like compiler is a step where you gradually lower IR from high level IR to low level IR. LLVM is a very low level IR. So usually we recommend that the lowering process is incremental. So you go from torch IR into operator level IR and then into some other IR, and then finally you might reach LLVM IR. So that's actually just kind of like hinting the path where the MLIR is taking, which basically it would got kind of like exported from A10 level IR into Torch MLIR, and then from there there's a path where you reach LLVM. Awesome. If that makes sense.
And another question, follow-up. How will the backend integration work with torch.export?
Okay, this is a very good one. So torch.export is still an effort under development, but the direction we're heading towards is it's going to produce a graph exactly at the same level like as the PT2 stack, that is after AOT autograd. So you can think of like the graph, the A10 FX graph used in PT2 stack, and then the torch export will have the similar set of characteristics.
Awesome. I think we're all caught
because they share the same front end, so they resulting in the same kind of graph. Okay, so let's resume. There's a few like good property about this graph that I want to show you. That is, like you see all these annotations for the tensors. Like these are the shape and D type. And basically, it's an indication to say, okay, this input has a float 32 type with this given shape. And it's not just shape, it's symbolic shape. Like, take a look at this input. This is the input that corresponds to our input tensor, which has a batch size and some hidden dimension. But like you might ask, how come we figure out that like this input could have a symbolic shape? Yeah, that's kind of like the magic of the fake tensor, and basically we can figure out that okay, this dimension of this tensor could have a symbolic shape. We kind of like propagate the entire symbolic shape information together with the D-type information throughout the whole graph, so that like intermediate activations also have the symbolic shape and D-type. Right. We believe that this is pretty useful for the backend to write their analysis paths, because many times we rely on symbolic shape and D-type. Right. So, so I won't dive into the detail of backward graph, but if you want to support training, yes, like there's a Jello backward for, and then there's the backward for linear. But yeah, it's still like you can use the same compiler that compiles the forward graph to optimize the backward graph. So another thing that backends will run into is that like PyTorch have a very large operator surface. Natalia mentioned there's a 2000 operator. Yeah, like if you look into the native function.yaml, which shows you all the existing A10 IRs that we have, there are multiple count. The way depends on how you count it. If you count the functional version of the IRs, there's like 12,000. If you count over all the overloads in place out variant, it adds up to 2,000. And it's very hard for a backend to implement all of them, and it's just unrealistic. So that's why we introduced a mechanism called decompositions. Like decomposition is a way where we map so many apps into a much smaller set of apps. And basically, the way that we do decomposition is we write Python function to represent the inner implementation of a composite operator with a set of more primitive operators. So actually, this might be most easily demonstrated with a sample. So just like consider that we still have the previous model, and now in the AOT autograph here, we're gonna enable some kind of decomposition. And for the sake of simplicity, we're just gonna take the same set of decomposition that Inductor was using, and then we say, okay, this is our default decomposition to run, and then let's just run all the decomposition that is used by Inductor, and then you should see the difference of the resulting graph, right? So notice that the A10.T is now replaced with permute, right? And then there's a A10.Jello. Now it's a bunch of like more primitive element-wise apps. So it's basically a way of mapping this like so many crazy operator into a more primitive set. And this set, we have kind of come up with a boundary for it. And later I'm going to talk about it. It's called A10 offset, right? And basically A10 offset is the recommended operator set for backend to interact with. But before that, I'm going to also just quickly touch upon like the decomposition that is passing into the AOT autograph here is configurable. Like the reasoning behind this is that all the backends actually have a slightly different need in terms of the offset. So it's not very reasonable for PyTorch to say we have to force everyone to use a single set of IR. But instead, what we come up with is a core collection of operators for the backend to interact with. So the idea being that like Inductor has a whole set of decompositions, and it works for us to write a whole compiler backend for it. So basically, you can use the same set of decomposition used by Inductor as the default, and that's your starting point to fine-tune the to adjust the decomposition so that you can fine-tune the resulting offset. But all this like variance of the resulting offset would kind of like are the variance of the A10 ops, which I'm gonna show you here. Like basically, like we have come up with the offset IR called A10 IR. This is a collection of somewhere around like 200 to 250 operators that still exist after decomposition. And all of these operators are functional because we have already run through the AOT autograph functionalization path. and this operator should have removed all its in place and out variants. And they are guaranteed to have the meta information propagation implemented for them, so that throughout the graph, you have the D type and the shape. Right. So effectively, as I've just mentioned, like this is also the output IR of the future torch.export path because they share the front end. And it's our recommendation that like graph-based backends can take this offset and start either export them into your own IR or implement the kernel based on these operators and plug into a PT2 stack. I want to pause here for questions.
So there is a question that came in, and it was the question I wanted to ask you if no one asked. The question is from Kazuaki. Some backend may want to undecompose, fuse a sequence of A10 prim IR in FX to one op. Example, softmax. Does each decomposed op have information to suggest the original op? So I guess some sort of like bookkeeping or where it came from, sort of.
Okay, there are twofold to this question. So first to start with, there is a way to stop decomposing the softmax, basically by adjusting the decomposition table. If you don't include the softmax in the decomposition table, then softmax would stay as softmax. But there are cases where you decompose, but somehow you still need to trace it back. There is a way to do that. And basically, we have annotations. It's not a very strong like guarantee that you always have this, but there is a meta field in the nodes for every like this decomposed op that you can use to trace back to the original A10 ops or the torch level ops. But it's not something that is like very, it's kind of brittle. So so take some caution if you want to rely on this path. Yeah.
Are there, I mean, this question from me, are there the original ops that can't be decomposed? Maybe you answered this, that would not be decomposed, in which case they would be part of the core set. Is that?
Yeah, so the core set is basically the operators that we consider are primitive and highly usable. Like, let me give you a very concrete example. So like originally you see A10.T, and then if you're familiar with the A10 offset, there's also A10.transpose. And now we say, okay, like both A10.T and A10.transpose will actually be decomposed into A10.permute. Why is that? Because permute is more generally usable, and there's a benefit for you to adopt the A10.permute op because Inductor is implementing on this set of A10 core IR, right? And basically these are the battle-tested decomposition paths. You are guaranteed to have the metadata information populated with it, so you have the best support if you take dependency on this offset. But it's not to say that you cannot come up with your own operator stats, but it's just that like you might need to implement your own meta function or other stuff. But another thing I want to mention here is like it's configurable. Like let's just say, okay, for some reason I don't want to decompose the AddMM anymore, and you can see that like AddMM now becomes stay as a single op instead of being decomposed. So we say both AddMM and the decomposed version, the A10.mm, are pretty reasonable for backend to support. And if you look into the IR, both of them are there, right? So like there are some wiggle room for backend to select like what are the operators that you want to work with. So that's the benefit of having kind of like a softness of IR where you have a rough like set of operators to work with, and there's a lot of flexibility on how you lower from the torch ops into your own IR.
So Sherlock, just a time check. We just have a couple more minutes left. This is such an interesting topic. I want to keep talking. I have so many other questions to ask you, and I'm sure the audience members too. Are there other key things that you want to cover? Maybe take one or two questions, and we'll have to.
Yeah. So unfortunately, due to time reasons, there's also another set of IR called prim ops. Like this op, this set of IR is more even lower level than A10 ops. They are even more primitive. So they are intended for compiler backend who care about having explicit type promotion and broadcasting. So it's also included in the doc here, so you can take a look. These are the prim ops. So just to call out like the explicit property of this op is that like they do explicit type promotion and broadcasting. And the example here would demonstrate that like a simple addition like this would actually be decomposed into 3 prim ops, where you have explicit type promotion and explicit broadcasting, and eventually a prim addition. So it's more for compiler backend who needs to have such explicit behavior explicit, and then somehow you have a powerful fusion that can fuse all of them together to reclaim the performance. So lastly, there's like 2 utilities that we don't have time to cover, but the example here.
Questions, if you want to answer those before we. I know this is an interesting topic. I want to keep going, but I want to be respectful of people's time too. So there's a question about this is an interesting one. Does PrimTorch IR support quantized ops and or quantization, basically ops?
At this moment, no.
At this moment, no. Okay, good. Yeah. Any update or info on mixture of backends?
Yeah, so the mixture of backend, it's something that we are exploring. So basically, at the backend interface, you see that, okay, you can have all these multiple backend that come together and work together. So it's something that we are thinking about, but there's no actual, we haven't started working on this.
Okay. 2 more questions, then we'll wrap up. There's a question: how's the progress of integrating AIT with this flow?
Wow, this is very deep.
Yeah, we need another show on this topic. I think if everyone agrees, we should 100% revisit this. I know we are 2 minutes over, but if you want to take this, and then we will wrap up.
Yeah, so AIT, it's referring here is called AI template. It's an internal deployment, internal runtime that mostly focus on the inference side. So we have been exploring how to integrate AIT into the PT2 stack, and basically we have tried both approach, like integrating at the FX graph level and also inside the inductor level.
Okay.
Yeah.
Oh, awesome. And last question: is there any specification regarding inductor loop level IR?
I think Natalia maybe can better answer this question, but like the inductor loop level IR are basically the ops dot something, ops dot load, ops dot add, like these things that like we overload for different operators. So I as far as I know, we don't have a doc to list out all this inductor level IRs. Anything you want to add, Natalia?
No, unfortunately, we don't have a doc. But yeah, that's correct. Those are the load store inner function that we've briefly touched upon.
That's the cliffhanger for today's live stream. You know, you're to wait for the next episode. We will wrap up now because we are 3 minutes over. But this was a very interesting stream. I wish we could have continued. There's so many questions I had. But let's do a follow-up one. We'll plan, and which brings me to the upcoming event. So please, if you're watching, please head out to pytorch.org/events. You'll see all the previous events. Also, upcoming ones will be updated here. So if we do decide to do a follow-up on one of these, which we might based on some of the interest and feedback here, you will find it on this page. So go bookmark this. The other place to find previous streams is YouTube. So go to YouTube PyTorch channel and you'll find questions. Sorry, you'll find the previous live stream recording, including this one after this show. So I want to thank all of you. I mean, thank you for all your time. I think this is very valuable. You're spending your time to answer questions from the audience here. Ben, Shalak, Natalia, Aiken Wang, from Intel too. Thank you so much for being here. And we'll close the stream here. Thanks again for attending, and look forward to seeing you again at future live streams. And see you until then. Bye.
Bye.
Thank you. Bye.
Bye.